Hello everyone, my name is Fangliang Zhong, and I'm a PhD researcher from the University of Nottingham. Today I'm going to give you a presentation about my recent research of exploring HVAC system operational fault impacts on energy demand and thermal comfort under current and future climate scenarios. Here is the outline of today's presentation. Let's start with the background. Building sector accounts for a large portion of world final energy consumption. According to International Energy Agency, 31% of world final energy consumption was attributed by commercial and residential buildings. These buildings are also responsible for more than 50% of the global carbon emissions. In terms of building energy consumption, HVAC systems account for the largest energy end use in both commercial and residential buildings, which is responsible for 57% in total. Based on energy consumption surveys conducted by US Energy Information Administration, HVAC systems account for 44% and 51% of the total energy use for commercial and residential buildings, respectively. Currently, operational faults are the major issues affecting the performance of HVAC systems. According to a survey in California, 65% of residential air conditioning units and 71% of commercial air conditioning units involved faults. Typical HVAC faults contain control faults, sensor faults, AHU faults, chiller faults, and etc. Due to these operational faults, HVAC systems consume additional 20% or more energy. Automated fault detection diagnostic methods are the current solutions to operational faults and their corresponding energy penalties. FDD methods have the potential to reduce HVAC energy consumption by 10 to 40%. There are three main categories of FDD methods: rule-based methods, model-based methods, and data-driven methods. To support the development of FDD, fault impact analysis is needed for the following reasons. First, it can help researchers identify the faults with significant impacts and prioritize these faults during the development of FDD framework. Second, it can also help researchers realize the significant impacts of some previously neglected or less emphasized faults, such as HVAC set point setback faults, and consider these faults in the FD framework. Third, there's a need to study the interactions among multiple faults and the combined effects of multiple faults on system energy and occupant thermal comfort. Now let me introduce the research gap identified based on literature review. Most of the previous fault impact studies focus on the impacts of single faults under the current or historical weather conditions, and only a few of them study the impacts of multiple faults. In addition, climate change has potential to affect the performance of HVAC systems in terms of energy and thermal comfort, and thus it may intensify the fault impacts. Based on the literature review, a conclusion can be drawn that currently there's no study exploring the fault impacts on HVAC system energy and occupant thermal comfort under future climate scenarios. The aim of this study is to assess the fault impacts on one of the most common HVAC systems, VAV system, under the current and 2030s and 2050s weather conditions, and also to investigate the effect of climate change on the fault impacts. There are four main objectives in this study. First, we need to evaluate the variations in system energy and occupant thermal comfort for each single or multiple faults from the baseline normal case under each climate period. And these variations are integrated into energy and thermal comfort indicators. Second, these indicators are used to rank the single and multiple faults respectively. Third, it also needs to study the relationships between actual combined effects of multiple faults on system energy and thermal comfort, and algebraic sums of these impacts of each single fault involved in each multiple faults case. Lastly, it also needs to assess the variations among different climate periods in terms of system energy and thermal comfort. Now let's move to the methodology part. As for fault modeling and simulation, there are four main processes. First, the fault model will be developed using Python based on fault definitions, characteristics, and mappings between faults and fault-associated parameters in Eng+. After the fault impact is formulated, the fault model will be validated using experimental data. Then, the validated fault model will be introduced into Eng+ prototype building model, which is also verified. Next, the fault simulation will be conducted on Eng+. We specify simulation weather files and settings. Lastly, the simulated data will be exported for fault impact analysis. These are the four models considered in this study and their corresponding fault intensities. In terms of fault impact analysis, first, there are three main parts. First, the fault impacts for each single or multiple faults were compared with that for the baseline normal case, and the deviation from the baseline normal case was integrated into energy and thermal comfort impact indicators. And these indicators are used to rank the single and multiple faults in terms of energy and thermal comfort, respectively. Second, the interactions among multiple faults are studied, and the effect of multiple faults can be divided into two types: synergetic effect and antagonistic effect. Third, the fault impact variations from current to 2030s and from current to 2050s are also evaluated. As for the indicators used for ranking the faults, the energy impact indicator was determined by the maximum value between the maximum of all the energy consumptions for each single or multiple faults and the total of all the energy consumptions. The reason for using this equation to calculate energy impact indicator is to not only highlight faults which have insignificant increases in all energy consumptions, but lead to a substantial increase in total, but also not to neglect faults which have decreases in most of energy consumptions, but led to a substantial increase in one particular energy consumption. As for thermal comfort impact indicator, it was calculated based on the predicted percentage dissatisfied for each zone under each fault case. Regarding to the interactions among multiple faults, the two effects of multiple faults are defined as follows. Synergetic effect is the effect when actual combined effect is greater than the algebraic sum. And antagonistic effect is the effect when the actual combined effect is less than the algebraic sum. As for the case study building, Eng+ median office prototype building was used and verified using previous results. It's a 3-story building with 5 zones on each floor. Regarding to simulation weather file, the current London Heathrow weather file was generated using median norm 8, and future weather files were obtained based on IPCC median emission scenario. For HVAC system, a combination of VAV system and package air conditioners are used. The VAV terminals are equipped with reheating coils, and the package air conditioners are equipped with cooling and gas heating coils. Now let's move to the results part. These are the top 7 single faults in the energy impact ranking. The fault with the most significant impacts under each climate period is all the same as supply fan stuck at maximum speed, which resulted in substantial increases in air system total, heating coil, cooling coil, and fan electric energy. As for the top 10 single faults in thermal comfort ranking, supply fan stuck at maximum speed also led to the most substantial deviation in PPD of around 9 to 10% under each climate period. Regarding to the energy impacts of multiple faults, synergetic effect can be observed in the deviation from HVAC sum for the top 5 fault combinations. The most significant variations in the deviation from HVAC sum can be observed from heating coil gas energy for the combination of cooling coil supply air temperature sensor positive bias and supply fan stuck at maximum speed. In addition, the combination of supply fan stuck at maximum speed and outdoor air damper stuck fully open also led to the most significant increase in the deviation for reheating coil electric energy. In contrast to synergetic effect, antagonistic effect can also be observed. The four combinations of supply fan stuck at minimum speed with outdoor air damper stuck fully open and with outdoor air damper stuck fully closed resulted in substantial decreases for heating coil gas energy. In addition, the combination of thermostat positive offset and supply fan stuck at maximum speed led to substantial decrease in the deviation from HVAC sum for reheating coil electric energy. As for the thermal comfort impacts of multiple faults, the combination of cooling coil supply air temperature sensor positive bias and supply fan stuck at maximum speed led to the most significant deviation in PPD of around 2% under each period. In addition, the obvious difference is that the variation in the deviation from HVAC sum in PPD for supply fan stuck at maximum speed and outdoor air damper stuck fully open decreased from 0.8% under current period to 0.3% under 2030 period, and further to minus 0.5% under 2050 period. Regarding to the fault impact variations for single faults across climate periods, heating coil gas energy, reheating coil electric energy, and the PPD decreased, while cooling coil electric energy and fan electric energy increased. For air system total electric energy, most of the single faults led to increases, but supply fan stuck at maximum speed, delayed evening setback, and no overnight setback resulted in decreases from current to 2030s period. As for the fault impact variations for multiple faults, similar trends to those from single faults can be observed. The only difference occurs at air system total electric energy, where almost half of the fault combinations led to decreases from current to 2030s period, especially for the fault combinations with supply fan stuck at maximum speed or no overnight setback. In addition, 3 fault combinations including no overnight setback still decreased from current to 2050s period. In conclusion, the key findings are as follows. First, supply fan stuck at maximum speed led to the most substantial increases in both energy and thermal comfort. Second, synergetic effect is most remarkable in heating coil gas energy and reheating coil electric energy, while antagonistic effect is only significant in heating coil gas energy. Third, heating coil gas energy, reheating coil electric energy, and PPD for all single and multiple faults decreased, while cooling coil and fan electric energy increased. For air system total electric energy, most of single and multiple faults increased, but some of them led to decreases, especially for the combinations with the no overnight setback and the single fault of no overnight setback. Future work can explore the fault impacts under different climate zones, such as tropical climate, and also fault impacts from other HVAC systems, such as variable refrigerant flow system, are worth to be investigated. Thank you for your attention. Please feel free to ask me any questions through the conference system or through emails. Thank you.